Alright, section 4.2, classifying chemical reactions. Here we've got some main large categories that we classify chemical reactions under, depending on what's happening in them. These are broad categories. There are further subcategories that we can classify them in sometimes, but we want to introduce at least the big ones for you here. So number one, precipitation reactions. Precipitation, as we talked about before, precipitation is the formation of a solid. It wasn't there before. When you mix these two solutions together, a solid forms, it starts falling out of the solution, if you will, and collects at the bottom of the beaker. That's a precipitate. Precipitate is the solid itself. And so precipitation reactions, again, a dissolved substance reacts to form a solid product or precipitate. These are also called double displacement reactions, double replacement reactions, or metathesis reactions. Other names for them. And before we talked about double displacement reactions without calling them that. We explained up here why these things form, or how they form. When I looked at this, I had an ionic compound. We talked about these swapped the positive and negative partners. In other words, in here the silver used to be connected to the nitrate, but instead the calcium, the positive calcium, comes and replaces it. So now the calcium is connected to the nitrate. Here the calcium used to be connected to the chloride, but the positive silver is going to come along, and now the silver is connected to the chloride. So, they're displacing each other, or they're replacing each other. Double displacement or double replacement reaction. Again, metathesis reaction is another way that that's referred to as. Alright, and so we need to know if this is going to happen or not by whether a precipitate will form. You see, if there's no precipitate that forms, if everything is soluble, well then, as the complete ionic equation would show, all of the ions are just existing in solution. All the ionic compounds have come apart to form those ions, and they're just out there swimming around in solution. You have the calcium before, you have the calcium after, nothing's changed, but it would be true for all species. And so that would actually be no reaction. They're just all there, they're just all swimming around together, but nothing's actually changing, right? That's technically no reaction at all. So for a metathesis reaction, or a double displacement reaction to occur, some precipitate has to form, or in some way there has to be some kind of a change, and it's usually a precipitate. So, solubility, whether something dissolves or not, is very important for this. And we define solubility as the amount in either grams or moles that will dissolve, and usually we're talking about in water. So how much will actually dissolve? Is it highly soluble, or is it not soluble, or very, very low soluble? We call it just soluble or insoluble. Again, they're not quite black and white like that. You have different gray areas where it dissolves just a little bit. It's slightly soluble. We're not going to get into that yet. That'll be a later chapter. Okay? But right now, just big soluble versus insoluble. So how do you know what is soluble and not? There are things called solubility rules. Right? And so, for example, here are the solubility rules as presented in this textbook. And honestly, I don't love this presentation of it. I'm going to show you a different one which I like better. But let's take a quick look at this. It says soluble compounds contain group 1 metals. Hey, that's like sodium and potassium and lithium, that first column on the periodic table. Let's call it up really quickly here. Whoops, I just hit the wrong button. I don't want that. I want my periodic table. There we go. All of these guys, so lithium, sodium, potassium, rubidium, cesium, those guys are for the most part going to form soluble compounds. All right. Ammonium, so NH4 plus 1, those are usually soluble. Halides, chlorine, bromine, iodine, those are usually soluble. So etc., etc. You can see these. Those are usually soluble with these exceptions, silver, mercury, and lead. All right. And so that's a good general rule, I guess. You can follow it. These guys are usually insoluble, carbonates, chromates, sulfides, phosphates, and hydroxides, with these exceptions. All right. They're correct. But I think they're a little hard to follow. What I prefer are the solubility rules as they're presented in the Chempendix, which is on the Sapling website. Here's their solubility rules, and I also put these rules up on Moodle for you, so you can get them from there. They list them as just a list of 7 rules, and you simply follow them in order. So the very first rule you find that applies, that's the one you go with. All right. So example, the very first rule, hey, group 1 elements, Same kind of what we looked at before, right? Lithium, sodium, potassium, rubidium, cesium, and francium are all going to be soluble, as are ammoniums. They're soluble. Then rule number 2, if it's got a nitrate in it, or a chlorate, or a perchlorate, or an acetate, soluble. Chlorides, bromides, iodides, soluble, except for silver 1, lead 2, and mercury 1. And then it says, with the exception of rule 1, carbonates, chromates, phosphates, and sulfites are insoluble. They don't want. So, really, this, with the exception to rule 1, we've already seen rule 1. So, they really didn't have to write that. If you just take them in order, you've already applied rule 1 if it need be. Number 5, blah, 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 again, bariums. Rule 1 and barium. Hydroxides and sulfides are insoluble. And then they got this asterisk. Asterisk, we're just going to refer down to here where it says calcium, chromate. Alright, so it starts getting a little bit confusing here. Number 6, exceptions to rule 2, silver, mercury, and lead are insoluble. And then number 7, so we start getting more exceptions as we go to the lower rules. Usually, one of the first rules is going to apply. Right? And if that you don't like, they also have this nice little chart here where it lists all the various positive ions. Here's all the various negative ones, and if you mix and match it, whether it'll be soluble. Alright, so here's iron 2. If I mix that with a chlorine, I look down here, iron 2, and across here chlorine, so right there, hey, it's a white box. It's soluble. Whereas if I looked at silver and chlorine, I come across here, oh, it's a darkened out box. That would be insoluble. So you can always use this kind of a chart too, and it shows you whether it's soluble or not. Alright. And then there are some additional little notes on some of these, like the single asterisk talks about those, the double asterisk talks about magnesium sulfide. It actually decomposes in water. And then most oxides, these are the 3 asterisks here, they actually react with water to form hydroxides instead of saying just as oxides. Alright, so again, the first few rules, the big rules, fairly simple to apply. Then it gets a little trickier after that with exceptions to it. But be able to use these rules. Right? Now what I've done is to further take those and write them in a nice compact form, which again I've also put on Moodle for you. Alright, this is the one that I think is probably the easiest to apply, and if I need to go back and look at details, I can pull up those other rules. Right? So here again you apply them in order. The very first one that applies is going to be the one you use. Right? So let's do an example. Let's say I had sodium chloride, table salt. Now we all know that table salt does dissolve just fine in water. NaCl, so it's a sodium and a chloride. I would go to the solubility rules. Anything in group 1, hey, including, there we go, Na plus 1. Those are soluble. So there we go. I found my first rule that applies. Sodium chloride is soluble. Okay. Notice the strongest rules, right? The big ones here are rules 1, 2, and then most of 3. Those are all soluble. That's why I put them in green here for you. And look at the charges on those. Plus 1s all the way through here. These minus 1s all the way through here. Number 3, the soluble chloride, bromide, iodine, all minus 1s. For the most part, if you have a minus 1 or a plus 1 on the charge, it's likely to be soluble. If you have a plus 2 or a minus 2, not so likely to be soluble. Right? And so if you mix and match them, if they're both a higher charge, like a plus 2 and a minus 3 or something, likely insoluble. Right? And then somewhere in the middle on everything else. And so I can kind of take a guess at things right away. If say I think like copper iodide or something like that, CuI, right? Copper 1 iodide. Well, they're both plus 1 and a minus 1, and so I'm thinking soluble right off the bat. And sure enough, if I looked at this, the third rule would apply. Iodides are soluble. Now it says except for lead, mercury, and silver. So I do have exceptions, but my first guess would have been true. Copper iodide is soluble because it doesn't. And I don't have to go any further because I found the first rule that applies. All right. The exceptions, if you're trying to memorize this a little bit, again, plus 1s and minus 1s are pretty much soluble with the exception of this. So if I had lead 2 chloride, that would be insoluble because it's one of the exceptions here. That's why I put it in red. Lead, mercury, and silver, and this is like P and mercury and silver. There is a way that some people remember that. This is lead, mercury, silver. They call that PMS. The PMS is the exception to these being nicely soluble. I don't know if that helps you. I'll let you use that. It shows up down here as well. Insoluble down here, lead, mercury, and silver. So once again, PMS. And so if that helps you, great. Otherwise, I guess just use the rules. Insoluble ones. Let's look further. Carbonates, chromates, phosphates, sulfites. Look at those. They're all 2 minuses. I kind of would have predicted that those would have been insoluble then. Except for calcium chromate, which is slightly soluble. So it's even barely an exception at that. Let's see number 5. Here's a kind of a surprise one. Hydroxides, because it's a -1. So there's one of the big exceptions you might have to try to remember. Hydroxides, they don't fit our big rule of just being a 1. Right? But those are insoluble, as are sulfides. And then we got our exceptions. Except for barium. So you have barium hydroxide or barium sulfide. They're going to be soluble. Also, except for calcium hydroxide and strontium hydroxide, which are just slightly soluble. Alright, so again, it barely is an exception. Magnesium sulfide, we already, I think, mentioned that. That one actually just decomposes in water. So, well, it's soluble, I guess, or in some sort, but it quickly reacts and turns into something else. Insolubles, lead, mercury, and silver. Again, maybe a bit of an exception because silver is a +1, but it actually forms insoluble things, as long as one of the upper rules haven't applied yet, that is. And then here, another strange one here. Sulfates are usually soluble. Even though it's a 2-, they're usually soluble, with the exceptions of calcium, strontium, and barium. Okay, so to me, this kind of concise copy of them is the easiest and quickest to use, but again, I might have to go back and look at some more details if I need to on some of these. Let's try and apply this, because it's kind of confusing until you go ahead and use it. This example, we're going to react potassium iodide with lead 2 nitrate in water. So I wrote this out. Here's potassium iodide, K+ and I-, lead 2 nitrate. So lead in the 2+, nitrate is a -1, so I need 2 of those. So there we go, lead 2 nitrate. What's it going to form? All right, well, I'm going to swap the positives and the negatives, metathesis type reaction. So my potassium will now be connected to my nitrate. So there it is, potassium nitrate. My lead will now be connected to my iodide. So there it is, lead iodide. Keep the charges in mind. Make sure you have balanced things correctly. And now I have to think about, I started with soluble. I've formed these new things. Are they going to be soluble or not? Well, let's check them. Potassium nitrate. Right off the bat, I'm thinking soluble because I got a K+1 and a nitrate, which is a -1. So I'm thinking, yeah, probably soluble. But let's go back up and check. Oh yeah, rule number 1 right off the bat. Here it is, potassium, soluble. So sure enough, that one's soluble, so I can write an AQ after it. It's soluble. Lead iodide. All right, here's a -1, but then this lead, and oh yeah, remember lead, the PMS, that's often the exception here. So I'm thinking it would have probably been soluble, except I bet the lead changed it to insoluble. Well, let's go back up and check the rules. Alright, I've got nothing that applies in number 1. Number 2, nothing applies there. Number 3, ooh, here's an iodide. Remember, I'm looking for lead 2 iodide. So here it is, and it would be soluble with the exceptions of, oh, there it is, lead 2. So it's one of the exceptions. Yeah, lead 2 iodide is not soluble. Therefore, I write an S. It's going to precipitate out of solution and fall to the bottom of my beaker. Alright, if I was to write that now as an ionic equation, then I would separate it all out. The spectators would just be sucking around, so I'd cancel those or just not include them, and here would be my net ionic reaction. The lead is combining with the iodide to give me this solid. That's what's actually changing in that. Okay, there is your first class of reactions then. I scroll back up here, remember it was called precipitation reactions. Our classifying of chemical reactions, and the most important thing there is the solubility rules and knowing how to use them. Alright. My second, actually I'm going to stop.